Imagine for a second you're an engineer, and a really critical piece of machinery just breaks down. The problem? It's not in a workshop. It's orbiting Earth at 17,000 miles per hour in the freezing, totally hostile vacuum of space. You can't just send a mechanic. So how on earth do you fix a satellite from a million miles away? Well, let's dive into this.
You know, our whole modern world pretty much runs on satellites. They're this invisible backbone for our GPS, our communications, even how we predict the weather. But they are incredibly complex machines, and when something goes wrong up there, the consequences down here on Earth can be huge. So yeah, what happens when one of these vital machines starts to fail?
A lot of the time, the point of failure is a little thing called a reaction wheel. Now, the easiest way to think about these is like incredibly precise, super high-tech spinning tops that are inside the satellite. By just changing the speed of these spinning wheels, the satellite can pivot and aim itself with absolute pinpoint accuracy. And this is totally crucial for, say, pointing an antenna back at Earth, or a telescope at some distant galaxy. Now, according to the research we're digging into, these wheels usually suffer from two main types of faults. First, friction can build up, and that's often because the lubrication fails in the super harsh environment of space. Or, second, you can get a voltage surge, which creates this thing called back electromotive force, or EMF. That's basically fighting against the motor. Either one of those problems can send a satellite spinning completely out of control. So, in this explainer, we're going to break down exactly how engineers are tackling this problem. We'll look at why these failures are so catastrophic, check out the old, kind of inefficient ways of diagnosing them, and then get into a brilliant new three-step solution. We'll see how it did in testing, and then what it all means for the future of space missions. All right, first up, satellites on the brink. Let's really get a feel for how a tiny little failure can be an absolute disaster. The heart of the problem is that everything in space is just incredibly complex. The physics involved are what engineers call nonlinear, which basically means a tiny change can have these huge, unpredictable, cascading effects. And on top of that, satellites, especially the smaller ones, have very, very limited computing power. You can't just run some heavy-duty diagnostic software. You'd kill the battery. And that brings us right to our second section, the old way to fail. Let's take a look at why the previous methods just weren't cutting it. So one of the older ways to do this was to constantly run multiple diagnostic programs or filters at the same time, one for each possible problem. But as the paper points out, this is a massive drain on a satellite's limited computer brain. It's kind of like having every single warning light on your car's dashboard running a full diagnostic check 24/7. It's just not practical. Another huge limitation was that these systems needed what's called a priori knowledge. That's really just a fancy way of saying you had to program the satellite with exactly what every single possible fault would look like before you even launched it. So if some new, unexpected problem popped up, the system was completely blind. And maybe the most critical thing, they were slow. Now, 80 seconds might not sound like a long time to you and me, but for a satellite that's tumbling through space, 80 seconds is an eternity. By the time the system even figured out that something was wrong, the mission could already be toast. So the bottom line is we needed something smarter, faster, and way more efficient. And that brings us to the new approach that's outlined in this research, a three-step solution. I want you to think of it like a brilliant onboard detective, one that's always on the case. What's so amazing about this new process is its logic. It doesn't drain power by running all the time. Instead, it follows this really smart hierarchy. Step 1, detection, is the lookout. It's just monitoring for anything unusual, asking that one simple question, is something wrong? Only if the answer is yes does it activate step 2, isolation. This stage is the investigator. It uses some clever probability to ask, okay, which specific part is broken? Once it has a suspect, boom, it moves to step 3, identification. This is the analyst, figuring out the exact nature and severity of the problem. It's asking, just how bad is it? And this really shows the difference in a nutshell. The old methods were clunky. They were always on, they were heavy on resources, and they were slow to react. This new hierarchical method, it's elegant. It only turns on when it's needed, which makes it incredibly efficient. And because each step is so targeted, it's lightning fast.
So the theory sounds great, right? But does it actually work? Let's jump to section 4 and see how this system did when they really put it to the test. The headline result from all the simulations is pretty incredible. We're talking a 97% success rate.
To get a bit more specific, the researchers ran what are called Monte Carlo simulations.
This basically means they just threw thousands of different random fault scenarios at the system over and over and over just to see how it would hold up. And in those crazy intense tests, it successfully completed all 3 detective steps: detecting, isolating, and identifying the problem up to 97% of the time. I mean, that is an unbelievable level of reliability. If we dig in a little deeper, the study tested 2 common ways reaction wheels are set up. The first is a standard 4-wheel setup, which got an average accuracy over 93%. The second is what's called a pyramid configuration, and that was a bit lower, around 86%. So why the difference there? Well, it all comes down to geometry. The pyramid setup is more symmetrical. And what that means is that a fault in one wheel can sometimes create a physical effect that looks really similar to a fault in a different wheel, and that can occasionally confuse the diagnostic system. The standard setup, on the other hand, has less symmetry, which actually makes it easier for the system to pinpoint the exact source of the trouble.
And all of this brings us to our final section, smarter, safer space missions. What does a breakthrough like this actually mean for the future of, well, everything we do in space? The bigger picture here is just huge. It means satellites can become way more autonomous, diagnosing and even handling problems all on their own. This makes them more robust, less likely to fail. And for all of us down here on Earth, it means the technology we rely on every single day becomes more dependable. And this is so critical. It's what future-proofs space exploration. For those really long missions to Mars or probes going out past Jupiter where it takes hours for a signal to get back to us, this kind of onboard intelligence isn't just nice to have, it's absolutely essential. And this, right here, is the most important takeaway. This system doesn't just send an error message back to Earth saying, "Help," it's an integrated system. Once it finds a fault, it can actually help the satellite's main controls reconfigure themselves, adapting to the problem and working right around it. It's the difference between a system that tells you, "Hey, the engine's broken," and a system that says, "Hey, the engine's broken, so I've already rerouted power to compensate, and we can keep the mission going." This research is a massive leap forward in making our space systems smarter and more resilient. It moves us from just detecting faults to having true autonomous adaptation. And it leaves us with a really fascinating question. If a satellite can diagnose and reconfigure itself around a problem, how far away are we really from a future where they can truly heal themselves?